Hello everyone, very good evening. I welcome you all at India's most comprehensive preparation platform for all competitive exams, that is BYJU'S exam prep. So guys, in the last session, we have understood the concept of multilinear regression. This concept of ridge and lasso regression is also related to similar concept, that is multilinear regression. We will try to understand that what are the problems which we may face when we are simply using the cost function or the error minimization function with respect to multilinear regression. Okay, so this is brief introduction of myself. My name is Vishal Rawatiya. I have 10 plus years of teaching experience, and following are the achievements and areas of expertise. This is my Telegram group. If you guys have any doubt related to GATE preparation, whether it is CS paper or DA paper, you can ask me at this particular Telegram group. I'll be happy to answer all your doubts. Apart from that, you will get all these benefits on joining this Telegram group. So either you can use this link or you can simply search CS by Vishal Rawatiya. You should be able to find this group. Okay, so tomorrow, that is on 1st of October, BYJU'S exam prep is going to conduct a national scholarship test. If you participate in this test and do good, then you may avail up to 90% off on our programs which are going on. Apart from that, Rakesh Talreja sir is going to conduct a workshop on 4th of October. In this particular workshop, sir is going to discuss that what are the 7 prime qualities to top the GATE exam. So this will be a good session. You may analyze that how you can improve on those particular qualities so that you can also be in the list of toppers, right? So apart from that, this is high time. The October is about to start, so I will suggest you all that please sincerely participate in the test series which are going on. So this is the platform, this is the image from the leadership board of the BYJU'S exam prep test series. So you can also participate in the test series on the BYJU'S exam prep app. Now the link, whether you want to participate in this national scholarship test or you want to attend this workshop or you want to appear for the test series, you just need to download the application of the BYJU'S exam prep app. You just need to register yourself and you will be able to access all of them. Now, registration link is in the description. You can download the application using that link. Okay guys, let's start the today's session, that is ridge and lasso regression. So these are also known as ridge and lasso regularization, also known as L2 and L1. So ridge regularization is also known as L2 regularization. Lasso regularization is also known as L1 regularization. Okay, so just 1 minute. Yeah, fine, good enough. So in the yesterday's class, in the last session, we have already discussed the concept of multiple linear regression. What happens in the multiple linear regression? If there are 2 or more independent variables on which your dependent variable depends, then such type of linear regression will be known as multiple linear regression, right? What happens in the simple linear regression? Good evening, Fanto. In the simple linear regression, your dependent variable will depend only on a single independent variable. Clear? So please try to recall that the equation that we are going to use the similar equation again in the today's session. So what did we say? That the predicted value y is defined as what, sir? If there are multiple variables, let me write x1, x2, x3 up to xp. Let's say if there are p independent variables, on those p independent variables, if your variable y depends, then what will be the equation? What are you asking? Respect me. Operating system is taken by which faculty in paid batches? Respect me. I believe that operating system will be taken by Satya sir, I guess, right? So okay, so these are the p independent variables on which this dependent variable y is dependent. So please try to understand what happens. We are providing the weights to each one of this independent variable, that this, what is the weight of independent, what is the weight of each independent variable in order to identify the value of this dependent variable, in order to identify the value of this dependent variable, and it will be a simple linear equation. So please try to understand that in the terms of multiple variables, the equation is defined as beta 0, where beta 0 is the intercept. What can I call it? Intercept, right? Then beta 1 is the weight or coefficient with respect to the first independent variable x1. Beta 2 is the weight or coefficient with respect to second independent variable x2, and so on, right? So for the pth independent variable, the weight or coefficient will be beta p. This will be beta p with respect to pth independent variable. So what is this? So this value is the predicted value. This is the predicted output. If I want to define that this is the actual output when we are training the data, if I want to define this as the actual output, then I'll add this error term. I will add this error term, that with respect to this predicted output, what actually the error that should be added in order to get the actual value. So this is your predicted value without this epsilon. So let me, for understanding the concept, let me denote it using y hat. And y will be the actual value. Let's assume that y is the actual value and y hat is the predicted value. So how can I define the error function? What will be error? Error will be basically the actual value was supposed to be y. So this is your actual output. This is your actual output, and y hat is your predicted output. So whatever the difference is between actual output and predicted output will give you the error. Clear? I hope this much is clear to everybody. Yes, and what do we try to minimize? Sir, we try to minimize this error. But that is represented in the form of sum of squared error format. We try to minimize the sum of squared error. Clear? So that I'll explain in a while. I'll again write the equation, but this is your linear regression, that you will try to fit the input independent input variables on a line such that you can predict the dependent variable. This is the simple concept. This we have already discussed in the previous session. Now let's try to understand that why actually we need this ridge or lasso regression. Clear? Why do we need this regularization techniques? So please try to understand that there is one term which is known as overfitting. So what is overfitting? Please try to understand. If you try too hard for something, if you are trying too hard to achieve the result, then ultimately something may eventually go wrong, right? So that's the concept of overfitting, that if you are trying to fit the model too accurately, on the test data, then it may be possible that because it is too accurate on the test data, it may not perform accurately on the not the test data, training data. If you try to fit the model too accurately on the training data, then it may not perform accurately on the test data. What does it mean? Sir, you are trying to fit the model too accurately, then if a new input comes, then because this is too accurate with respect to given input, and it is not trying to generalize the model, therefore it may not behave properly with a new input, with respect to new input. Clear? You will understand in a while that what is happening. So what is an overfitting scenario? Overfitting, an undesirable machine learning behavior that occurs when the machine learning model gives accurate prediction for the training data. So you are training it too much. Clear? Covers all the points without any. Yeah, correct. Or yes, correct point. Covers all the point without any correct direction. Yes, obviously you can think of that in that particular direction as well, right? So it's too accurate with the training data, but not for the new data. That is not for the test data. When you are trying to test that particular model, that how good is this particular model, then it will not perform well with the test data. Clear? Why? Because the focus was too much on the training the particular thing. I'll explain the example and you will realize that yes, it may actually happen. Right? Now, overfitting model can give inaccurate predictions. Yes, because on what? It can give inaccurate predictions on the new data. It can give inaccurate predictions on the new data. So overfitted model can give inaccurate prediction and cannot perform well with all the types of new data. So whenever you are giving a new data, so it is happening with a single input, then we can tolerate it. But if the prediction is not accurate with all the new inputs, then the situation is worrisome, right? So that's the logic, that if your model does not predict the correct value for any of the new data, then you are in trouble. If it is not predicting the correct value for one or two of the input, but predicting the correct value for remaining input, then it's fine. Clear? Okay, so what do we try to do? Now let me define that when we are trying to understand the concept of multiple linear regression, we try to minimize. What do? We try to minimize sum of squared error. Yes or no? That's what we do. So our focus is on to minimizing it. So we will try to attain a value when the sum of squared error is 0. That's what we do, right? We try to differentiate it, we try to partially differentiate it with respect to different parameters, and we try to identify the different values of different parameters such that the sum of squared error is 0. We are trying to minimize the sum of squared error, then our ultimate goal is to make it equivalent to 0, right? So what is sum of squared error? Sir, first of all, let's assume there are an input. Let n observations, I would say n observations. So what will happen? Let's assume with respect to observation I, with respect to any observation I, if the result was supposed to be yi, so we are denoting the actual output using y, and we are denoting the predicted output using y hat. So the idea is, if your actual output was supposed to be yi, but it happened to be yi hat, if it happened to be yi hat, then this is your error. This is your error, and we are actually trying to minimize the sum. So this is your error, and if you square it, then this is the square of the error, and we are trying to minimize the sum of the squared error. We are trying to minimize the sum of the squared error. So there are n observations, so you will eventually try to minimize with respect to all these observations. Clear? But please try to understand, when you are writing yi, when you are writing yi, good evening sir, Anand sir, very good evening. When you write yi will be, this is the predicted output, right? So yi will eventually have all this coefficients, yes or no? So when I'm writing it yi, then yi can actually be written in this particular format. Yi can be written in this particular format, that what is the beta 0 value for I, what is beta 1 x1 with respect to I, beta 2 x2 with respect to I, and so on. Clear? So this is your sum of squared error, where this yi can again be written as, what? Sir, it is actually nothing. If I try to write y, then I can write the y. Let's look at this. I can write this value in what format? I can write it as summation. How many variables are there? So the variables are pi. So I can write it as 1 to p. I can write this y as 1 to p because there are p variables. And then beta I, because with respect to 1 it will be beta 1, and this is xi, beta I xi. So you can again write it like this. Clear? Clear? So y can also be written in this particular format. So here you can replace this yi hat. You can replace this yi hat using this particular form. Clear? Anyway, so this is the overfitting. Let's try to learn more about overfitting. So you only get accurate predictions if the machine learning model try to generalize all types of data within its domain. Please try to understand. If you are trying to fit the data too closely, your model will not work correctly. So though we say that our motive is to minimize this sum of squared error, but if your result is making this result as 0, if your model is trying to make this sum of squared error as 0, then most probably you are eventually going to the under or overfitting. Clear? So please look at this. You only get accurate predictions. These are predictions. So the predictions will be accurate if your model is generalized. It means your model is trying to generalize the scenario. If you are trying to fit every element too closely, or you are trying to fit every training data too closely into the model, then you are not trying to generalize. You are just interested in fitting the training data into the model. You are not trying to generalize it, that what will happen if a new input comes. Clear? So you only get accurate predictions if the machine learning model generalize all types of data within its domain. If it tries to generalize, then only you will get the accurate prediction. Overfitting occurs when the model cannot generalize. Overfitting will occur when the model cannot generalize and fits too closely to the training data. So when you are trying to fit too closely with the training data and you are not trying to generalize the model, then the situation of overfitting will arrive. So please try to understand, these are the different models. Oh sorry, these are the different input. If you are trying to fit too closely, with them, and if a new input arrives, then you will not be able to fit it. That's the problem, that if you are not generalizing the model, if you are eventually trying to generalize it like this, then you will be able to predict that, okay, what will be the value, right? And the prediction will be more accurate compared to this model which is fitted too closely. Clear? So that's the aspect of overfitting, that if your focus is too much on the training data, and if you are not worried about that what will happen with the test data, then overfitting scenario may occur, right? So why does overfitting occur? Please first of all try to understand that why does overfitting occur. So overfitting may occur because of various reasons. One is the training data size is too small, that is the observations which are available with you to train the data are very limited. So if the observations are very limited, you will try to fit very closely with those observations. Very obvious that if you have only 2 observations, let's assume if you have only 2 observations, you will always fit it accurately using this line, right? But if a new input comes, then you are not trying to generalize the model, that what may happen with the different values of input, So it's a new input, so it will not fit well with your model which is too accurate on the input data. So generally when the training data size is too small, your model will try to fit too closely with that training data. Clear? Another is the training data contains large amount of irrelevant information. When we say large amount of irrelevant information, so please try to understand with an example. That if we are talking about that how the prices of houses are varying in a city in last 20 years. So if we focus on one thing, that salary increase, how salary is increasing, how population is increasing year by year. Please try to understand the concept. So your price of houses in a city price of houses in a city may vary with the increase in the salary, with the population increase. As the population grow more and more, the space available to fit all of them will eventually become less, and ultimately the prices of houses will shoot, right? But what is the average temperature throughout the year? If you are also trying to fit this particular input in your model, then how exactly the price of houses will depend? How exactly the price of houses will depend on the average temperature throughout the year? I mean, it's not relevant in order to identify the variation in the prices of houses. Clear? So the training data contains large amount of irrelevant information. So there may be some features in the input. There may be some features in the input on which the actual output is not dependent that much, right? So if you are trying to fit those things also in your model, then the overfitting may be possible, right? So training data size is too small, then overfitting may be possible. Training data contains noise, so it can actually be treated as noise, that some wrong information. You can also say wrong information is available. So you are trying to, if you are trying to model with the wrong information, then ultimately output will also be wrong. Another thing is the model trains for too long on a single simple set of data. If you keep training on a very small, so if you are keep training it, keep training. So it will eventually try to learn that, okay, this is the ultimate data. Whatever I want to do, I need to produce the right result on this input data set only. So if you keep training, then model will adjust itself according to that input data. Yes or no? If you keep training the model on the same data, then over the period, your model will learn everything about that data. Yes? And ultimately, when a new data arrives, it will not be predict the correct output. It will not be able to predict the correct output. These are the reasons because of which the overfitting may occur. Now, if I try to give you an example of overfitting, please try to understand. So this, overfitting and underfitting with the context of high bias, low bias, high variance, low variance. It seems a question in the GATE exam. There may be a question, I assume that there will be a question from the concept of overfitting or underfitting in the GATE. Clear? So that's why I'm explaining this much rather than explaining the concept of ridge and lasso, because the idea is these are the mathematical equations. Most of you may not understand them. So I'll just give the brief about those ridge and lasso expression. But the very first thing which you need to understand is that why these regularizations are required. Why these regularizations are required. So let's try to understand that we are trying to, our machine learning model is trying to predict that a photo is of a dog. Please. You are eventually trying that your model learns to predict whether the photo given to that particular model, is the photo of a dog or not. Getting the idea? Now please try to understand. When you are training that model, please assume that when you were training that model, then all the photos which were given to that particular model were of the dogs which were in a garden or in a lawn. Clear? So ultimately, image processing will not only try to process the image of the dog, the shape of the face of that particular dog, but if you keep training over the images in which the dog is sitting in a garden or the dog is sitting in a lawn, then ultimately your model will also try to model the grass available in the background in the picture. So your model will learn that whenever a dog will be there, this green color grass should also be there. Yes or no? Yes or no? Because your model is trying to learn from the similar type of images in which behind the dog there is grass all the time. So all the pictures which were given to that particular model as an input were having grass or a lawn or a garden behind the dog, or the dog was sitting in a garden or a lawn. So ultimately, your model will think that this grass should also be taken care of. So your model will start learning that, okay, this grass is also important. So whenever I want to predict that, yes, this is a dog, I should also think of this grass, right? So all of a sudden, if you provide a picture to that particular model in which the dog is inside a room, it may fail to say that it is a dog. Getting the idea? Because there is no grass around it. So the model has learned in a peculiar manner in which there was always grass around the dog. Yes or no? Do you realize that the model was trying to fit in too closely with the input, or too closely with the test data, and in all the test images the grass was there, right? So model will try to analyze this grass should be there in every image of dog. So all of a sudden, if the picture of a dog is from a closed room, the model will fail. It will eventually tell you that no, it's not a dog because there is no grass. Clear? Clear? So that's the law. That's just an example. I was just trying to give you an intuition that how exactly a model can learn something noisy. The model can eventually predict that noise is also important for the purpose of modeling. Clear? So this is the concept of overfitting. Right? Now, apart from that, please try to understand what will happen. So let's try to understand one simple concept. What if model, this is example is done. Example is done. I am trying to give you some other information. So if model works too accurate with the test data, if the model works too accurate with this test data, then it is called low bias. Then the model is called low bias. Okay. If model does not work accurately with a test sorry, I am saying, why do I get confused again and again? This is training data. Sorry. In the very first statement also. So if model works too accurate with the training data, then we say that the model is having low bias. If the model does not work accurately with training data, then we say that the model is high bias. Then we say model is high bias. Apart from that, two more things. So this is related to bias. These two terminologies are related to bias. So bias is defined based on the training data. Bias is defined with respect to training data, right? So now if I say, if model works too accurate, if model works good with the test data, so it's working good, not accurate. It will not be accurate enough. But if model works good with test data, when you are trying to test your model, if your model is working good on the test data also, then we say low variance. So low variance will be there when your model is more generalized. Low variance will be there when the model is more generalized. It means it has generalized from its learning that yes, if you provide me a new input, then also I'll be able to give you the correct result. Now, if model does not work good with the test data, so if model does not perform well with test data, so means it varies from the actual result. So we say high variance. Then we say high variance. Please try to understand. Please try to understand what is termed as overfitting. What actually is termed as overfitting? If your model is too accurate with training data, means it is not trying to generalize the input, it is eventually trying to fit accurately with the training data, then we'll say it has low bias. So in overfitting model, what will happen? In overfitting model, the model will work too accurately with the training data, but whenever a new input comes, it will fail. Whenever a new input here does not perform well with test data, so whenever a new input comes, it fails, then it will be the situation of overfitting. So what's the scenario? For overfitting, the bias should be low and variance should be high. For overfitting, it will be low bias. That means it performs too good with the training data, but high variance, it means it does not perform good with test data. Right, so this is the concept of overfitting. The another term which is not that important, because I mean, if you are not putting enough efforts, then you are going to get bad result, right? But what is happening in overfitting? You are putting too much efforts. Because of that, you are not getting good result. In overfitting, you are putting too much effort on training the model. Therefore, you are not getting good results on the test data. But what if you are not training the model enough on the test data itself? If you are not training the model enough on the test data itself, so I mean, it has not learned anything. Your model, if you are not trained the model enough, then your model has not learned anything. So the model has not learned anything from the test data, then if the model has not learned anything from the training data, then how the model is supposed to produce the accurate result on the test data? Yes or no? So overfitting is something in which your focus was too much on the learning. That means you are trying to your machine or your model was trying to learn too hard from the data which was available for the purpose of training. Therefore, this problem is arriving that it's too it is fitting too closely with the training data. But another terminology which is known as underfitting. So in underfitting, when is the scenario of underfitting? When you are not giving enough time to the model for the purpose of learning, then it has not learned anything, or it has not learned sufficient from the training data. If the model did not learn sufficient from the training data, then how the model is supposed to produce the correct result for the test data? Obvious सी बात है, राइट? अगर आपने मेहनत नहीं की है तो रिजल्ट खराब आएगा, लेकिन अगर मेहनत की होती, ज्यादा मेहनत कर ली होती, तो फिर वो प्रेशर के कारण की बहुत पढ़ लिया है, प्रेशर के कारण खराब रिजल्ट आ रहा है, तो वो ओवरफिटिंग है, ओवर स्टडी, ओवर कॉन्फिडेंस, कुछ भी कह लो, ठीक है? अंडर कॉन्फिडेंस, पढ़ाई कुछ भी नहीं है तो रिजल्ट भी खराब ही आएगा, वो वाली कहानी है. सो अंडरफिटिंग इज अनदर टाइप ऑफ एरर दैट अकर्स व्हेन द मॉडल कैन नॉट डिटरमाइन अ मीनिंगफुल रिलेशनशिप बिटवीन द इनपुट एंड आउटपुट डेटा, कैन नॉट डिटरमाइन द मीनिंगफुल इंफॉर्मेशन बिकॉज इट डिड नॉट लर्न इनफ. So what's the idea? You get underfitted model if they have not trained for the appropriate length of time on a large amount of data points. So if you did not train the model for enough amount of time so that it can gather some meaningful information from that particular input, then ultimately if the model did not learn, then it is supposed to produce the wrong result on a new data also. Yes or no? So that's the concept of underfitting. So what is underfitting? In underfitting, let me write here. In underfitting, your model will not work good with the training data, your model will not work good with the test data because it did not learn anything. It did not learn anything. So, I mean, if it is not good on the training data also, so if model does not work accurately with the training data, it will said to have high bias, right? And it is not working good on the test data also, therefore high variance. So if the bias is high as well as variance is high, then it will be the scenario of underfitting. High bias plus high variance. Now your question may be, sir, what do we call it when the bias is high but the variance is low? It's not a practical scenario. You may say that, sir, what will happen if the bias is high, that is, it is not performing well with the training data, but it is performing well with the test data. How is it possible? Someone who did not study enough is not going to crack the GATE exam out of luck. Yes or no? So if you did not give sufficient time for the model to learn, then ultimately it is not going to produce the correct result for a new input, right? If you did not practice enough on your PYQ, you are not going to get the correct answers in the GATE exam also, right? So when you are not training appropriately, the output of the test will also be inconsistent, right? So this is the idea. So high bias, low variance will not happen. High bias, low variance will not happen. What do we need? Sir, we need low bias, that yes, the model works accurately with the training data, as well as the model should work good with the test data also. So low bias plus low variance is what is needed. Low bias. So we don't need overfitted model. We don't need underfitted model. We need generalized model. Yes or no? We don't need overfitted model. We don't need underfitted model. We need generalized model. What do I mean by generalized model? That it is working well with the training data as well as it is working well with the test data. So this will be the scenario when the bias will be low. Low bias plus low variance. Our model should be generalized model. Yes or no? Clear? Model should be generalized model. I hope you understand. At this point of time, you are able to understand that yes, if we are trying to make this sum of squared error as 0, if we are trying to make this sum of squared error as 0, then we are trying to fit too closely with the training data. Yes or no? Please try to understand. If you are trying to make this sum of squared error as 0, then you are trying to fit your model too closely with the training data. This is important. If you don't understand this statement, even after this much discussion, then you are not following the things. Our objective is to minimize the error. Our objective is to minimize the error, but don't minimize it that much that the model becomes overfitted. Getting the idea? Our objective is to minimize the error, but don't minimize it up to that level that the model becomes overfitted. Clear? Clear? This statement is clear that our objective is to minimize the sum of squared error, but don't make it 0. Most of the time when this squared error is 0, your model is most of the time overfitted. Clear? Because it was trying to adjust too much with your training data. Clear? That's the logic. So we don't want this to be 0. We don't want this to be 0, because if it is 0, then please assume that the model is toward the direction of becoming overfitted. Clear? So this is basically the cost function. This is the cost function. We try to minimize the cost. This is also known as cost function. This is also known as cost function. We try to minimize the cost. Clear? So that's okay. We have understood the concept of overfitting. We have understood the concept of underfitting. Now the question is, how can we prevent overfitting? How can we prevent overfitting? So if it is 0, then it is dependent. Dependent in what sense? If it is 0, then dependent on what? If it is 0, then it is overfitted. If it is 0, then it has learned too much from the training data and it has adjusted itself such that the error is 0. It has learned too much from the training data and it has adjusted itself such that the error is 0. Means it is trying to fit too closely with the input data. That's the logic. Now, how can we prevent overfitting? So, two concepts are very, very simple. First one is early stopping. What does it mean by early stopping? Before, I just told you that there may be some noise in the data, just like the grass in the background, just like the grass in the background of a image or pic of a dog. Yes. So before your model try to learn from that particular noise available in the data, please stop training the model. Don't train it for too long. Otherwise, it will learn from the noise also, and it will try to interpret the noise available in the data as the actual data, and it will try to learn from that noise as well. What the idea? Don't train your model for that long that it tries to learn, that it starts learning from the noise. Clear? When I say early stopping, then don't train for too long. So when I say early stopping, don't train for too long. So that don't train for too long. Otherwise, it will start accommodating noise of the data. Clear? So don't train it for too long. Another is feature selection. Just like I gave you the example that if this feature, that is average temperature throughout the year, is also available, then please tell me what is the use of this particular feature in order to identify the prices of house? Will it be that important? Yeah, it's okay that if weather is good, then in that particular city price will be high, but still it is not that important. If there is no money flowing in the city, then what's the point of good weather? Yes, please try to understand. The simple example is Andaman and Nicobar, right? So the weather is too good, everything is beautiful about that particular location, but there are not enough resources for people to earn. So if there is not enough money flowing in, then how come the prices of houses will grow? Simple analysis, right? So that's the idea, that these are two most important things. If the population is not enough, what will you do of the houses? The land is, there will be enough barren land that you can build house wherever you want. So why the prices of houses will grow if there is not enough population? If the salary is increasing, means if the money is flowing in, then only the prices of houses will grow. So these two factors will eventually, on these two factors, the prices of house will be highly dependent, but the prices of house will not be dependent that much on this average temperature of the year, right? So these are the features. There are three features in the input data on which your output may depend, but some of the features may not be important. So eliminate such features. So it is known as feature selection or pruning. What does it say? That remove independent variables which does not influence the dependent variable significantly. right? So these are the two aspects. Apart from that, the third one is known as regularization. The third one is known as regularization. So what do I mean by regularization? So there's Ridge and Lasso regularization, or Ridge and Lasso regression, or L2 and L1 regularization. So these are the regularization techniques. These are the regularization techniques. So now we are going to talk about this regularization technique. So what do I mean by regularization? Regularization refer to a technique that are used to calibrate the machine learning models. They try to calibrate the machine learning models in order to minimize the adjusted loss function and prevent overfitting. That means we do not try to minimize the actual loss function, or we do not try to minimize the actual cost function, or we do not try to minimize the actual error, but we try to minimize the adjusted error. We try to minimize the adjusted error, clear, such that the overfitting is prevented. So these are the models, these are the techniques which will try to modify your cost function, they will try to modify your loss function, they will try to modify your error function such that the overfitting is prevented. So the idea is, if you are minimizing the error itself, then your objective will be to minimize the error to 0. In that case, it will become overfitting. So rather than minimizing the actual error function, we'll try to minimize something else. We'll try to minimize something else. Manish, jaldi aayega beta. We'll try to minimize something else. So there are two regularization techniques. Mainly there are others, but mainly there are two regularization techniques. One is known as ridge regularization, which is also known as L2 regularization. So if somebody says L2 regularization, so please try to understand that is talking about ridge regularization. Lasso regularization is also known as L1 regularization. And these are also known as ridge or lasso regression. मनीष, आई ट्राई माई बेस्ट, है ना. वैसे भी यहाँ पर आप देखो, थोड़ा सा मुझे टेलीग्राम पे मैसेज करो, मैं आपको बता दूंगा. आप तो वैसे भी कनेक्शन में हो, तो यहाँ पर इस चीज को देख लेंगे. ठीक है. अनदर, चलो लेट्स स्टार्ट. सो देयर आर टू मॉडल्स, देयर आर टू regularization technique. Why do we use the regularization technique? To prevent overfitting. Why do we use them? Ridge or lasso? We use ridge or lasso to prevent overfitting in the multiple linear regression model. The models which are using the concept of multiple linear regression, in those models we are trying to avoid the overfitting. Clear? So what happens in the ridge regularization? So we just need to understand the expression. We just need to understand the expression of ridge and lasso. We have understood that why these regularizations are required. We have understood that why these regularizations are required. The only thing left is to understand that how this regularization will try to avoid overfitting. Clear? So in ridge regression, the cost function is basically what? Cost function is sum of squared error. When I say cost function, it's nothing but sum of squared error. Rather than saying sum of squared error, they call it cost function because it may change, right? So sum of squared error will be nothing but the sum of squared error. Therefore, they define it as cost function. But okay, this is the cost function which we are trying to minimize. Clear? So in ridge regression, the cost function is altered. We will change it. So we'll change from sum of squared error to something else by adding a penalty. So we'll add a penalty. Because of that penalty, this error will never come down to 0, because you are not trying to minimize this sum of squared error which defines the error, but you are actually trying to minimize this plus something. So when you are trying to minimize this plus something, then some weightage is given to some other things also. That means you are not only trying to minimize this, but you are trying to minimize a new function. So in ridge regression, the cost function will be altered. It will not only be the sum of squared error, but it will include some penalty. And that penalty will try to that penalty will try to avoid the overfitting. What will be the penalty? The penalty will be equivalent to the sum of square. The penalty will be equivalent to sum of square of the magnitudes of the coefficient. Obviously, even if you don't write it magnitude, then also because of square, it will become positive. Because of square, it will become positive. So please try to understand what will be the new cost function. What will be the new cost function? So we already have a cost function. What? For n data sets, we have a cost function I equals to 1 to n. If there are n data points, then we are trying to minimize yi minus yi hat square. Where earlier we were trying to minimize this. Earlier we were trying to minimize this, but now we will not try to minimize this. We will add a penalty. We will add a penalty. So we will not try to make this 0, we will try to make this overall summation as 0. So when we are trying to make this overall summation as 0, some weightage is given to this penalty also. Some weightage is given to this penalty also, means this thing is not actually coming down to 0. This thing is not actually coming down to 0. A new thing is coming down to 0. What is that new thing? You will understand that something, just add randomly some value and try to make it 0 will not work. Just try to add some random things into the actual cost function and try to make it and try to minimize it will not work. So what actually happens? We add something which is known as lambda times sum of beta I. These are nothing but these are what? Beta I are the magnitudes of the coefficient. Magnitudes of the coefficient. The beta 1 is the coefficient of x1, beta 2 is the coefficient of x2, beta 3 is the coefficient of x3. So we are sum of the square. So first square it. A square of the magnitude, this is the sum, this is the square of the magnitude, we need to sum it. So how many elements will be added? Sir, there are p. Please try to understand. In my example, I have considered p independent variables. So this p is what? Number of independent variables. This p is actually nothing but number of independent variables. So we are trying to add the sum of the squares of the coefficients corresponding to each independent variable. So this p is number of independent variable. So please try to understand what is this. Please try to understand. If I write it, then this thing is actually nothing but lambda times. This thing is actually nothing but lambda times b1 square plus beta 1 square plus beta 2 square plus beta 3 square. So this is up to beta p square. Beta p square. So these are basically the weight. I mean, you can call them slope, you can call them weight, you can call them coefficient, whatever you want. Whatever you want. Please try to understand in a simple line, what does the slope represent? What does the slope represent? Slope will represent what? That if you change x by 1 unit, if you change x by 1 unit, sorry, this is 1. If you change x by 1 unit, how much change will be visible in your y? If you change, what is slope? Slope is nothing, but if you change x by 1 unit, how much change will appear in your y value? So it's actually, this slope will eventually give you what? The weight of that particular variable x. The weight of that particular variable x. That by what factor this actual value y will vary with that particular variable x. So if the slope is more, then the significance of that particular variable will be more in order to determine the value of y. If the slope is less, if the slope is almost slant, then even if you move by 100 units, in x direction, the variation in the y side will be very less. So if slope is low, if the slope is low, then the importance of that particular variable will be very less in order to identify the output. But if slope is high, then that particular variable will highly correlate with your dependent variable. Got the idea? Got the idea? So you can call them slope, you can call them coefficient, you can call them weight of individual variable, that how large is the weight of a particular variable. So as this value increases, then ultimately per unit in a change of a unit in x direction, the change in y direction will increase. So as the weight of an individual variable or the coefficient, as the coefficient increases, then it means that the weight of that particular variable is more in order to determine the actual output. Yes or no? Yes or no? So that's the logic, that this coefficients are added. So please try to understand. Okay, that's it. I just wanted to give you the intuition that how the slope will eventually be useful in this calculation. But please try to understand what will happen here. This lambda is training parameter. You can call it training parameter. The value of lambda may be anything between 0 to infinity. The value of lambda may be anything between 0 to infinity. As the value of lambda increases, then what will happen? See, please try to understand. Something whose value is very low, the variables whose coefficients are almost, variables whose coefficients are almost equivalent to 0, if we multiply them by a large value, then also their weightage will be almost 0. The coefficients which are large, if they are multiplied by a large value, then their importance in order to predict this value will increase. Yes or no? So, and when the lambda value is equals to 0, actually equals to 0, your ridge regularization will eventually behave as normal. Your ridge regularization will degenerate into simple multilinear regression, because in that case, when the lambda value is 0, this thing will not be present. And we are simply trying to minimize this sum of squared error. And if we are simply minimizing this sum of squared error, then this is as good as your multilinear regression. Yes or no? So the values of lambda may be anything between 0 and infinite. As the value of lambda increases, it will also perform the task of feature selection. That is, the variables whose coefficient are almost negligible will be almost removed from the modeling, and the variables whose coefficient are large will eventually have more and more weightage in the learning rate. Yes or no? So this is also known as parameter with which your model will learn. The parameter with which your model is learned. So it's an hyperparameter which is used for the purpose of feature selection. That can be used for purpose of feature selection, and this particular thing will eventually try that the model is not overfitting, because we are not trying to minimize the actual error, we are trying to minimize something else. So if we are trying to minimize this thing will never become 0. So if this thing is not becoming 0, and we are also giving the weightage, to the independent variables on which the output is highly correlated, then ultimately the model will be more generalized. We will eventually remove those variables who are very slightly affecting the actual output. Clear? So that's the concept of ridge regularization. So this is basically with respect to ridge regularization. What you need to remember, what's the basic difference in ridge and lasso? In ridge regularization, we are adding the penalty in the form of sum of square, of the magnitudes of the coefficient. And in Lasso, the only difference will be, that the penalty that is being added is nothing but the sum of the magnitude of the coefficient. We are not squaring it up. We are simply adding the magnitudes of the coefficient. So what will be the new cost function becomes? What will be your new cost function in this particular case? New cost function will be original square, sum of squared error will already be there. So this will become yi minus yi hat square. I guess I used the same variable. I can call it j. So that you do not get confused between these two I. I can call it j so that you do not get confused between these two I. So one is I, another is j. I is eventually defining the number of observations. J is defining the variables. Okay, so this is I. Let's try to add. So this is your sum of squared error. This is sum of squared error. We are not trying to minimize this only. We are trying to minimize lambda times sum. So we are saying sum. So first of all, it will be sum of what? It will be sum of magnitudes of the coefficients. So the coefficients are beta j. So we are summing up the magnitudes. So when we are summing up the magnitudes, let's take modulus. When we are summing up the magnitude, let's take modulus, and we are saying that we are summing up for all the coefficient of all the variables. So it will become, how many variables are there? So there are p variables. Clear? So this is your cost function with respect to Lasso regularization or L1 regularization. So we'll try to minimize this. We'll not try to minimize the sum of squared error only, but we'll try to minimize this. Try to minimize this new cost function. Similarly, in in Ridge, try to minimize this new cost function. There will be no difference in learning mechanism. You will just try to partially differentiate it with respect to beta 0, beta 1, beta 2, etc. And you will try to minimize this. So you are not trying to minimize this thing only. You are trying to minimize this overall equation. This lambda will be, as you change the value of lambda, your model will learn differently. As you change the value of lambda, your model will learn differently. So you will keep changing the value of lambda. You will keep training the model. You will eventually adopt the value of lambda such that there will be low bias and low variance. What? You will keep changing the value. You will keep changing the value of lambda. You will keep training your model. You will adopt the value of lambda when the model is having low bias and low variance. Clear? So for the different values of lambda, the values of coefficient will also change. Please try to understand. If you take lambda equals to 1, the values of coefficient will be something else. If you take lambda equals to 2, the values of coefficient will be something else. If you take lambda equals to 3, the values of coefficient will be something else. So you will try to train the model with different values of lambda, and you will ultimately select the lambda value for a model with respect to which the variance is low as well as bias is low. Clear? Because this type of model we want in which the bias is low as well as variance is low, because this will be a generalized model. Clear? Please tell me, clear? Do you want to ask anything else in this concept? If you have already studied it from somewhere else, and if you guys are facing any difficulty, then please let me know. You want some other clarity in this particular concept? See, numerical can be asked in this particular concept that you can have one or two, you can have two or three, not more than two or three, otherwise the things will become complicated. So you may have two or three independent variables and they may ask you to train based on some 4 or 5 inputs. Clear? So these are the models. Regularization. See, more important thing is that why are we adding this penalty? The most important thing is why are we adding this penalty? Because if we try to minimize this, then your model may be too fitted with the training data, and if the model is too fitted with the training data, then ultimately there will be overfitting. Clear? So we don't want overfitting. So your ridge regularization is used for avoiding the overfitting and also multicollinearity. So if there are variables which are dependent, highly correlated with each other, they will also be eliminated using this particular approach. In lasso regularization, we will avoid overfitting, as well as it can also be used. There may be some coefficient which will be negative. There may be some coefficient which are negative, but here we are adding the positive coefficient. So some of them may eventually become zero. So it means the weightage of those particular feature will become zero. So lasso regularization may also work for feature selection, right? It may eventually eliminate some of the features which are not that important. Clear? So this is it for ridge and lasso regularization. If you guys have any doubt, then you can ask me at this particular Telegram group. I'll share the PPT of this particular session in this Telegram group. So please join the Telegram group so that you will be updated with all the information. Clear? Apart from that, tomorrow we will try to understand the concept of logistic regression. So generally, regression is used when the output is a continuous variable, but here in logistic regression, it's basically a classification. Mostly it is used for the purpose of classification. The term regression may be here. The term regression is here in this particular notation, but it is mostly used for the purpose of classification. Logistic regression is mostly used for the purpose of classification. Please. Classification means you will have fixed set of outputs. Based on your input, you will select one of the category that in which particular category this input will belong to. Clear? So that's a classification problem. In continuous or real valued problem, your output variable, that is your dependent variable, may take any real value, right? It's not predefined. It may take any real value. It will not fall into any predefined category. That's the basic difference between classification and regression. So if you like the video, then please hit the like button. If you are new to the channel, then subscribe for the channel and press the bell icon so that you can get the notification about such wonderful upcoming videos. That will be all for this particular session. Thank you very much. Good night. Take care. Keep learning.